let's move to the basics of probability. So today we are going to talk about a basic framework which will model a probability experiment. What do you want to achieve using probability? Our main objective in probability theory is to compute the chance of an experiment, or more precisely, compute the chance of an outcome in a experiment where the outcomes are randomized in some sense. So this is what we want to achieve. For example, if I think of experiments, it could be tossing a coin, it could be throwing a dice, or it could be picking a random number from the interval 0 to 1. I have chosen 0 to 1, but it could be any other interval. And these are the examples of some experiments. And in these cases, the outcomes we might be interested in are, let's say, head when we toss a coin, occurrence of a prime number when we throw a dice, or when we are picking a random integer. When we are picking a random number between 0 and 1, let's say the number is bigger than 3 by 4. So these are the kind of outcomes we might be interested in given an experiment. And in high school, we had a very basic rule which said that the probability is equal to number of favorable outcomes divided by total number of outcomes. And most of the questions were solved applying this formula. What we need to do is to define the words in this formula more precisely. So our next goal is to define words like favorable outcome, even the word outcome, experiment more rigorously. This is what is going to be our first aim. And this is done by something called the sample. So the first observation we are going to have before we define sample space is that for an experiment, we really do not care about the physical implementation. When we toss a coin, whether Amitabh Bachchan is tossing a coin or Dharmendra is tossing a coin, is it on the top of the roof? We don't care. We will mostly bother about the possible outcomes. So in all these cases, the outcomes are heads or tails, except when it's tossed by Amitabh Bachchan. But let's assume that it is heads and tails. And then, what is the chance or frequency or the probability of these outcomes? As a mathematician, these are the interesting things to us. So this is what we care about. Physical implementation, we won't bother. Okay. Once we know this, then the importance of sample space kind of comes out. What is a sample space? It is just the set of all possible outcomes in a randomized experiment. So we want to model a random experiment. So first thing is to say what are the outcomes we can achieve. Mathematically, sample space is a set and is denoted by the symbol omega, big omega. To start with, you can think about the sample space for tossing a coin, throwing a dice, or our favorite experiment of picking a number between 0 and 1. So in all these cases, what is the sample space? Pause the video and make sure that you can figure out the sample space here. Once we have defined the sample space, the next thing is events. Mathematically, it is just a subset of a sample space. I should say sample a subset of the sample space omega. Intuitively, it is the set of things or outcomes whose probability we might be interested in. You remember, like a prime number or two heads or these kind of things. So all of these could be events and not just elements of the sample space. A thing to note here, most of the sample spaces in this course are going to be discrete because this is a course for computer science and mostly we encounter discrete sample space. And for this case, the probability can be modeled easily. So let us model probability for this case. When the sample space is discrete, the important thing is what we call a probability distribution function. Remember, we wanted to model an experiment. We started with sample space, events, which were all the subsets of the sample space, and finally, last but not the least, probability distribution function. This will model our probability event completely. So what is a probability distribution function? Not surprisingly, it is a function from omega, our sample space, to real numbers such that it satisfies two properties. One, if you look at the probability of any element in the sample space, it should be in 0. And second important thing, if I sum this probability over all elements of sample space, then this should come out to be 1. So any such function is a probability distribution function. This way, we will model our experiments where the sample space is discrete. We will talk about a more general framework in the next lecture, but let's stick to it at this point. So remember, to model, we need sample spaces, sample space of the experiment, then the events are all possible subsets of that sample space, and then we talk about probability distribution function, which is a function from omega to the real number which satisfies these two properties. This is a complete model of a probability event in probability. To start, you can think of an example. Suppose we toss two coins, or let's change it. We toss a coin twice. It has 10% probability of getting tails, let's say. So it's a slightly biased coin towards head, and we are interested in finding the probability that we get two consecutive heads. So we toss this coin twice and we want the probability of two consecutive heads. In this case, you should figure out what is the sample space and what is the probability distribution. This should be our goal in almost all the probability problems. Given any probability problem, your first goal should be to figure out at least mentally what is the sample space and what is the probability distribution function. Let us take a more practical example. Suppose your cousin is a gambler and she proposes the following thing to you. She will pick a random number between 1 to 1000. You can say that you have cards on which 1, 2 up to 1000 are written, and you or she will pick a random card. If the number is divisible by 2 or 5, then you win. That means she pays you 100 rupees. On the other hand, if that doesn't happen, if the number is not divisible by 2 or 5, then you will pay her 200 rupees. So Question is, should you accept this bet? Again, you pick a random number between 1 and 1000, and then if the number is divisible by 2 or 5, then you get 100 rupees. If the number is anything else, then you lose 200 rupees. Would you want to place your money on this kind of a bet? Our first goal should be to find the sample space. The sample space is pretty simple in this case. It is a set of all numbers from 1 to up to 1000. These are the all possible outcomes we have. And then the next step is to find probability distribution function. Again, we assume that all the numbers come up with equal probability. That means probability of omega should be 1 over 1000 for all omega in this sample space. So W would range from 1, 2, 3 up to 1000. For each of them, the probability is this. This implies that probability of a subset of, let's say, T of the sample space, this would be the size of T divided by 1000. And what T are we interested in? T is the set of all numbers n such that n is divisible by either 2 or 5. Now, as a small exercise, you figure out that the size of T is 600. So this is something which you can figure out. This implies that you get 100 rupees with probability 3 by 5 and lose 200 rupees with probability 2 by 5. Your winning probability or odds is 3:2, but you lose in 2:1 ratio or 4:2 ratio. That means you should not accept this bet, and obviously your cousin, proficient gambler, is trying to trick you. We should not accept this bet. It's a simple question, but again, make sure that you understand how we define the sample space and probability distribution.